20,000 light-years from Earth, there is a star so large that if it replaced our Sun, its surface would extend beyond Saturn. Every planet in our solar system would be buried deep inside it. Its name is Stephenson 218 shines, with the power of 500,000 suns but almost invisible. A wall of cosmic dust hides it, completely revealing itself, only to instruments that can see heat instead of light. And if we nearly missed the largest star ever discovered, what else is out there, still unseen? Subscribe for more stories hiding in the dark. Our Sun measures 864,000 miles across. A car traveling at highway speeds from one edge to the opposite edge would need 553 years of continuous driving to complete the journey. Already, this defies human comprehension. Nobody has ever driven for 5 centuries. Yet, that's merely the distance across one ordinary star among 200 billion in our galaxy. Stephenson 218 is 2,150 times wider. When astronomers first calculated this, using data from the Gaia satellite, combined with infrared observations, several independent research teams ran their analyses multiple times because the results seemed too extreme. They checked for instrumental errors, examined whether cosmic dust might be distorting measurements, wondered if perhaps they were observing multiple overlapping sources appearing as a single object. Every check confirmed the same conclusion: this single star genuinely measures 2,150 solar radii across. Consider what would happen if we performed a cosmic replacement surgery. Remove our Sun from the center of the solar system, that familiar yellow star that has warmed Earth for 4.5 billion years, that enabled the origin of life and sustained every organism that has ever existed on our planet. Now position Stephenson 218 in exactly the same location, centered at the gravitational heart of our planetary system. The transformation would be apocalyptic beyond imagination. Earth orbits at 93 million miles from the Sun, a distance astronomers call 1 astronomical unit. Light traveling at 186,000 miles per second takes 8 minutes 20 seconds to cross this gulf. Under Stephenson 218, Earth's entire orbital path would lie 400 million miles deep inside the star itself, buried beneath layers of increasingly hot plasma. Our planet wouldn't be orbiting, it would be vaporized, disassembled atom by atom, with those atoms then ionized into a plasma of naked nuclei and electrons at temperatures reaching millions of degrees. The atmosphere would be stripped away in microseconds. The oceans would flash to steam, then dissociate into hydrogen and oxygen, then ionize. The rocky crust would melt, vaporize, become indistinguishable from the stellar material surrounding it. Mars orbits at 142 million miles, roughly 1.5 times Earth's distance from the Sunday. Under Stephenson 218, Mars would suffer the same fate, existing only as a diffuse cloud of iron, silicon, and oxygen atoms mixed into the stellar atmosphere. The red planet's famous dust storms, its ancient river valleys, its polar ice caps of frozen carbon dioxide, all would vanish in an instant, reduced to atomic constituents floating in a sea of plasma. The asteroid belt occupies the region between 200 and 300 million miles from the Sun, containing millions of rocky fragments ranging from dust grains to Ceres at 570 miles across. Every single asteroid, from the largest down to particles smaller than sand grains, would be completely engulfed and vaporized. The belt itself would cease to exist as discrete objects. The rocks would first melt into droplets, then vaporize into atomic gases, then ionize into plasma, their material joining the vast reservoir of superheated matter, making up the star's bulk. Jupiter orbits at 484 million miles from our Sunday. This gas giant contains 318 times Earth's mass, features a storm system called the Great Red Spot that has raged for at least 300 years and measures wider than our entire planet. Jupiter generates more heat internally than it receives from the Sun due to gradual gravitational contraction. You could fit 1,321 Earths inside its volume. Yet under Stephenson 218, even Jupiter would be completely swallowed, its hydrogen and helium atmosphere mixing with the stellar plasma, its potential rocky core dissolved and ionized. The Great Red Spot, that hurricane larger than Earth that has persisted for centuries, would dissipate in seconds. Saturn orbits at 886 million miles, taking 29.5 Earth years to complete one orbit. Its ring system, composed of countless ice and rock particles ranging from micrometers to meters in size, extends outward from the planet in a disk so geometrically flat that if you scaled it to the width of a football field, the rings would be thinner than a razor blade. Under Stephenson 218, Saturn would sit right at the stellar surface, its rings almost certainly disrupted by intense radiation and gravitational stresses. The planet perhaps partially engulfed in the star's diffuse outer atmosphere, where densities drop to less than the best vacuum, achievable in laboratory chambers on Earth. Volume scales with the cube of linear dimension. When you double a sphere's radius, volume increases eightfold. When you increase radius by a factor of 10, volume grows by a factor of 1,000. When radius increases by a factor of 2,150, volume explodes by a factor of approximately 10 billion. 10 billion suns could fit inside Stephenson 218's volume, not stacked efficiently, but literally filling the same space simultaneously. Earth's current human population numbers about 8 billion people. If you gave every single person alive their own complete star identical to our sun, one personal stellar furnace for every man, woman, and child, across every continent, every island, every settlement, you would distribute 8 billion suns. Stephenson 218 could contain all 8 billion plus 2 billion more, enough for every human who has died in roughly the last century. Evolution never equipped our brains to comprehend billion-fold differences, because nothing in our ancestral environment varied by such extreme factors. We can write the numbers, can perform calculations with them, can understand them abstractly as mathematical objects. But we cannot truly feel what they mean. The way we feel the difference between holding one apple versus 2 apples. The star's energy output matches its physical scale. Stephenson 218 radiates somewhere between 440,000 and 630,000 times more energy than our sun, though measuring luminosity through dense dust clouds introduces significant error margins. Taking the middle estimate of 500,000 solar luminosities means this single star produces more energy every second than 500,000 suns burning simultaneously. In 1 hour, Stephenson 218 releases more energy than our sun produces in an entire year of continuous fusion reactions. All of human civilization, every fire ever burned, every engine ever run, every power plant ever built throughout all of recorded history, has consumed vastly less total energy than this one star releases in the time it takes you to snap your stock fingers. Yet despite this prodigious energy output, despite shining with the combined brightness of 500,000 suns, Stephenson 218 remains invisible to human eyes and to optical telescopes. Across 20,000 light-years, a distance so vast that light itself requires 20,000 years to traverse, it exists vast clouds and lanes of cosmic dust, microscopic particles of carbon silicon, and various minerals ejected from previous generations of dying stars. These dust grains, each measuring perhaps a micrometer across, exist in such tremendous numbers that they collectively block visible light while allowing infrared radiation to pass through with less obstruction. The phenomenon resembles observing a bonfire through a mountain rather than around it. The fire burns intensely, releasing light and heat, but with solid rock between you and the flames, visible light cannot reach you because it interacts too strongly with matter.
However, you might detect warmth through the rock if the fire burns hot enough and long enough, because heat can conduct through solid material over time. Cosmic dust acts similarly. It scatters and absorbs visible light very efficiently, preventing those photons from reaching our telescopes. But infrared radiation, with longer wavelengths, interacts less strongly with dust grains and can penetrate the clouds. Charles Bruce Stephenson, conducting a survey of stars in the constellation Scutum in 1990, noticed a cluster that appeared unusual. One particular star showed up as barely more than a dim smudge, invisible light photographs so faint it could easily be mistaken for an imaging artifact. When Stephenson examined the same position using infrared sensors designed to detect heat rather than visible light, the instruments registered an enormous thermal signature, indicating something far more massive and energetic than the dim, optical appearance suggested. For nearly 3 decades, this mystery object sat in astronomical databases, clearly significant but poorly characterized because the technology needed to measure it precisely didn't yet exist. The breakthrough came with the Gaia satellite, a European Space Agency mission launched in 2013, with the goal of mapping positions and distances of over 1 billion stars with unprecedented accuracy. Gaia measures stellar positions so precisely it could detect the width of a human hair from 1,000 kilometers away. By combining Gaia's distance measurements with detailed infrared observations from ground-based telescopes and space observatories, astronomers finally characterized Stephenson 218 properly. The data revealed not just a large star, but the largest star ever measured, an object so immense it challenges theoretical models of stellar structure. The numbers describing Stephenson 218 inspire awe, certainly, but they should also inspire confusion and concern among astronomers. According to our best understanding of how stars work, according to equations refined over a century of observation and validated against thousands of stellar measurements, this object should not exist at all. The physics governing stellar structure imposes hard limits on stellar size, and Stephenson 218 exceeds those limits by margins that should be impossible. So what happens when a star breaks the laws we thought were absolute? What happens when nature decides our rules don't apply? Stars exist in a state of constant battle between two fundamental forces. Gravity, responding to the star's mass, pulls everything inward toward the center, trying to compress all that material into the smallest possible volume. Radiation pressure, generated by nuclear fusion reactions in the core, where hydrogen atoms are forced together into helium, pushes outward in all directions. In a stable star, these forces achieve exact balance. Gravity, pulling inward, equals radiation, pushing outward, and the star maintains constant size, neither collapsing nor exploding, sometimes for billions of years. This balance has limits determined by physics. As a star increases in mass and size, fusion reactions in its core must intensify proportionally to generate enough radiation pressure to counteract stronger gravitational force from all that additional material. More mass means more gravity, which requires more fusion, which produces more radiation. The relationship isn't linear. Small increases in mass require disproportionately large increases in energy production to maintain equilibrium. Eventually, at a certain threshold, radiation pressure becomes so intense it overcomes gravity and blows the star's outer layers completely away into space, preventing the star from holding itself together despite gravitational attraction. This theoretical maximum is called the Eddington limit, named after British astrophysicist Arthur Eddington, who first calculated it in the 1920s. The Eddington limit represents the point at which radiation pressure from the star's energy output exceeds gravitational force, holding the outer layers down, causing the star to eject mass through intense stellar winds until it drops back below the critical threshold. Most theoretical models, incorporating decades of refinement and validated against countless observations, suggest stars cannot stably exist beyond roughly 150 times the sun's mass, typically corresponding to radii around 1,500 times solar radius, depending on temperature and evolutionary state. Stephenson 218 has a radius of 2,150 solar radii. It exceeds the theoretical maximum by approximately 50%, measuring 150% of what should be the impossible upper limit. The star is too large to exist according to equations that have successfully described every other star we've measured, too massive to remain stable according to principles governing stellar structure throughout the galaxy. Yet there, it sits 20,000 light-years away, burning steadily, apparently stable, completely indifferent to the rules it violates. At this very moment, 20,000 light-years away, iron is accumulating. The clock is ticking. The countdown has already begun. And when that clock reaches zero, when the iron core crosses a threshold calculated by physics with absolute precision, what follows will be one of the most violent events the universe can produce. An explosion so powerful it will be visible across the entire galaxy, bright enough to cast shadows on Earth at night, despite 20,000 light-years of distance and walls of dust thick enough to hide the star completely right now. The situation resembles discovering an animal that weighs more than skeletal structure should support biology. tells us bones can only bear certain loads before fracturing, which is why elephants represent approximately the maximum size for land animals and why the largest creatures ever to exist. Blue whales, measuring up to 100 feet long and weighing 200 tons, live in ocean water, where buoyancy provides support that bones cannot. Finding a land animal weighing as much as a blue whale would overturn fundamental principles of biomechanics. Finding a star 50% larger than the Eddington limit should be impossible, according to stellar physics. Astronomers have proposed several potential explanations. Perhaps the star rotates extremely slowly, minimizing centrifugal forces that would otherwise add to outward pressure and increase instability. Most massive stars rotate rapidly with surface velocities, sometimes reaching hundreds of kilometers per second, because they form from rotating gas clouds that conserve angular momentum as they collapse. If Stephenson 218 formed under unusual conditions, resulting in very slow rotation, that might provide additional stability, allowing it to grow larger than normal. Measurements of rotation are difficult for such distant objects, especially through obscuring dust, so we cannot yet confirm or rule out this possibility. Alternatively, perhaps the star loses mass extraordinarily rapidly through stellar winds, streams of particles blown off the surface by radiation pressure, at rates keeping it perpetually just barely below the threshold where it would tear itself apart completely. Massive stars routinely eject material through stellar winds, sometimes losing an Earth's worth of mass every few thousand years. If Stephenson 218 ejects mass fast enough, it might maintain precarious balance, constantly shedding outer layers, while fusion in deeper layers continues generating energy. Observations do detect evidence of mass loss, though quantifying the exact rate through intervening dust remains challenging. The third and perhaps most unsettling possibility is that our models remain incomplete, missing some physical process that only becomes important at these extreme scales. Most of stellar physics was developed studying normal stars, objects like our sun, or somewhat larger, and then extrapolating those principles to extreme cases. Extrapolation always carries risks. Physical processes that seem negligible under normal conditions might dominate at extremes, while effects that appear universal might break down when pushed to limits we rarely observe. Perhaps something about how radiation interacts with matter at these tremendous scales differs from predictions, or perhaps magnetic fields generated in the stellar interior contribute structural support in ways current models don't account for. What makes this possibility particularly humbling is that it would mean our understanding of stars, built over centuries of observation, theoretical development, and careful comparison between predictions and measurements, remains fundamentally incomplete despite all that effort. We're not missing some minor detail or small correction factor. We're potentially missing entire physical processes important enough to allow stars to grow 50% larger than our best theories predict. The universe operates according to principles we can't yet imagine, contains surprises hiding in regimes we haven't fully explored. The star's energy output presents its own physics problems that compound the mystery. Stephenson 218 radiates somewhere between 440,000 and 630,000 times the sun's luminosity, yet its surface temperature measures only about 3,500 Kelvin, actually cooler than many kitchen ovens, cooler than welding torches, cooler than the filament in an incandescent light bulb. This temperature paradox arises because of the star's sheer size. Nuclear fusion in the core generates energy at tremendous rates, creating photons that carry heat outward toward the surface. But the path from core to surface spans such an enormous distance, billions of miles, rather than our sun's mere few 100,000 miles, that photons lose energy along the way. Photons are absorbed and re-emitted countless times by atoms in the stellar interior, scattered and redirected through plasma storms, larger than Jupiter, delayed for hours or even millions of years in their journey from the fusion furnace to open space. In our sun, a photon born in the core takes approximately 100,000 years to random walk to the surface, bouncing between particles trillions of times before finally escaping into space. In Stephenson 218, that journey could take millions of years. By the time energy finally reaches the surface and escapes, So much time has elapsed and so much energy has been distributed across such vast surface area that temperature drops dramatically despite tremendous total power output. The result is a star glowing deep red rather than blue-white, radiating most energy in infrared wavelengths invisible to human eyes, appearing cool despite being one of the most powerful energy sources in the galaxy. If you could somehow survive close enough to see Stephenson 218 directly, without intervening dust, without radiation, that would kill you instantly, without gravity that would tear you apart, you would see a vast crimson sphere, filling your entire field of view, glowing like a coal in a dying fire, rather than blazing like a welding torch. Cool surfaces radiate much less energy per unit area than hot surfaces. A surface at 10,000 Kelvin radiates roughly 8 times more energy per square meter than a surface at 5,000 Kelvin, and about 50 times more than a surface at 3,500 Kelvin. Stephenson 218 achieves 500,000 solar luminosities, despite its cool surface temperature, purely through having surface area so immense that even relatively low energy, radiated per square meter, adds up to staggering total power when multiplied across billions of square miles of glowing plasma. This creates another physical problem. With such low surface temperature and such tremendous size, the outer layers of Stephenson 218 should be extremely unstable, prone to violent pulsations and massive eruptions that would shed the star's outer envelope in catastrophic episodes. Many red supergiants do exhibit this kind of instability. Stars like Betelgeuse show irregular brightness variations and dramatic changes in size as their outer layers expand and contract. Some models suggest Stephenson 218 might be undergoing similar variations, but we simply haven't observed it long enough to detect them. The star might pulsate with periods of years or decades, slowly brightening and dimming, but from our perspective, with only a few decades of data, it appears stable. Despite all these theoretical concerns, despite exceeding the Eddington limit, despite having a cool surface that should be unstable, despite violating multiple predictions from our models, Stephenson 218 continues existing, continues fusing elements, continues radiating 500,000 solar luminosities into the darkness of space. The star doesn't care about our equations. It doesn't concern itself with limits we've calculated or principles we consider fundamental. It simply exists, burning steadily 20,000 light-years away, completely indifferent to being impossible. Stephenson 218 won't continue burning forever because stars this massive face a death sentence written into their very nature, an inevitable, catastrophic failure that's already in progress deep within the star's core right now. Destination 4, the Iron Curse, 1930 to 2900. Tone-building, dread inevitable doom. Energy, medium-high, dramatic tension. The universe operates according to cruel irony when it comes to stellar lifespans. The biggest stars live the shortest lives burning themselves out in cosmic eye blinks, while their smaller cousins persist for aeons. Our sun has been fusing hydrogen into helium for approximately 4.6 billion years, and will continue doing so for another 5 billion years, giving it a total main sequence lifetime of roughly 10 billion years. Red dwarf stars, those dim embers, smaller than our sun, burn their fuel so slowly and efficiently they can persist for trillions of years longer than the current age of the universe, by factors of hundreds. The smallest red dwarfs currently burning in our galaxy will outlive every other star, will continue fusing hydrogen long after giants like our sun have died and cooled to darkness. Stephenson 218 has been burning for perhaps 10 to 20 million years total, and what remains of its life can be measured in hundreds of thousands of years, at most, possibly far less. The star could die tomorrow, could die in 1,000,000 years, but on cosmic timescales spanning billions of years, the difference is negligible. 10 billion times larger than our sun in volume, but will live 500 times shorter, like a mayfly that grew to the size of a skyscraper, but retained the mayfly's brief existence. This tremendous disparity arises from fundamental physics of how stars generate energy. Stars burn through nuclear fusion, combining light elements into heavier ones, and releasing energy in the process. The most common reaction fuses hydrogen nuclei single protons into helium nuclei containing 2 protons and 2 neutrons. This reaction releases about 0.7% of the mass involved as pure energy. Our Sun converts about 600 million tons of hydrogen into helium every single second, losing roughly 4 million tons of mass in the process. As that mass transforms into the energy we receive as sunlight, the rate at which fusion occurs depends extremely sensitively on temperature and pressure in the stellar core. Small increases in core temperature produce dramatically higher fusion rates, because reaction probability increases exponentially with the energy of colliding nuclei. More massive stars have stronger gravity, compressing their cores to higher pressures and temperatures, which causes fusion to proceed much faster. A star 10 times the Sun's mass fuses its fuel roughly 1,000 times faster, while a star 100 times solar mass might fuse at rates millions of times higher. Stephenson 218 with its tremendous mass burns through nuclear fuel at rates our Sun could never achieve, even if it continued fusing for the entire age of the universe multiplied by billions. While our Sun has been patiently converting hydrogen to helium for 4.6 billion years and still has most of its hydrogen remaining, Stephenson 218 exhausted the hydrogen in its core in just a few million years. Roughly the time complex life on Earth took to evolve from single-celled organisms to the first simple animals crawling on the ocean floor. After burning as a blue supergiant for those initial millions of years, incredibly hot and compact compared to its current state, the star depleted its core hydrogen supply and began the transformation into the red supergiant we observe today. When hydrogen fusion in the core ceased because all fuel had been consumed, leaving behind a core of helium ash, from millions of years of fusion reactions, gravity began compressing that helium core, crushing it to higher densities and temperatures. Meanwhile, hydrogen fusion continued in a shell surrounding the depleted core processing hydrogen that hadn't yet made it to the center. As the helium core contracted and heated under gravitational compression, it eventually reached temperatures around 100 million Kelvin, hot enough for helium fusion to ignite, combining 3 helium nuclei into 1 carbon nucleus. When the core began fusing helium, releasing new energy, the outer layers of the star expanded dramatically, swelling to enormous sizes while simultaneously cooling, as that expansion distributed the same energy output over vastly larger surface area. The star transformed from a compact blue giant, perhaps a few times larger than our Sun, into the bloated red supergiant we see today, with radius 2,000 times solar. This expansion occurs because of how energy transport works in stellar interiors. In very massive stars, energy generated in the core moves outward primarily through radiation, photons traveling through the star and gradually working their way from center to surface. But in the cooler outer layers of red supergiants, radiation becomes less efficient, and convection takes over with hot gas, physically rising to the surface, cooling, and sinking back down like water boiling in a pot. Currently, Stephenson 218 is fusing helium in its core, combining those helium nuclei into carbon and oxygen. Eventually, perhaps it's happening already. Perhaps it will begin in thousands of years. The helium will be exhausted, and a new phase will begin. The carbon-oxygen core will contract under gravity heating until it reaches temperatures around 600 million Kelvin, hot enough for carbon fusion to begin. Carbon nuclei will slam together with such force they overcome their mutual electromagnetic repulsion and fuse into heavier elements neon, magnesium, oxygen. That fusion will proceed for perhaps a few thousand years before carbon is exhausted. Then oxygen fusion will begin, lasting mere years. Then silicon fusion, lasting days. Each successive fusion stage produces less energy, requires higher temperatures, and lasts for shorter times as the star races through the periodic table at accelerating pace. This cascade of fusion reactions creates a layered structure inside the star, like a cosmic onion with different elements fusing in concentric shells at different temperatures. The outermost layers still contain hydrogen never heated enough to fuse. Below that, a shell where hydrogen is actively fusing into helium. Below that, helium fusing into carbon. Deeper still, carbon fusing into neon and magnesium. Then oxygen fusion producing silicon. Each shell operates at different temperatures and pressures. Each contributes to total energy output, each supports the weight of all layers above it. At the very center, in the core, where temperatures reach billions of degrees and pressures exceed anything we can create in laboratories, iron is accumulating. Iron, the element that ends the fusion chain, the poison that kills stars, the ash that cannot burn. Every fusion reaction up to iron releases energy because it produces nuclei more stable than the reactants. Hydrogen to helium releases energy. Helium to carbon releases energy. Carbon to oxygen, oxygen to silicon, silicon to iron, all release energy, creating pressure, supporting the star against gravitational collapse. Iron occupies a special place in nuclear physics. It is the most stable nucleus, the element with the highest binding energy per nucleon. You cannot extract energy by fusing iron into heavier elements. Such fusion would require energy input, would consume energy rather than producing it. For a star, iron is a dead end. When silicon fusion produces iron in the core, that iron cannot be fused further. It simply accumulates layer upon layer, atom by atom, building up a growing sphere of iron in the star's center. No fusion reactions can occur involving iron to generate pressure, supporting that mass against gravity. The iron core is inert, dead, supported only by electron degeneracy pressure, a quantum mechanical effect where electrons resist being compressed beyond a certain density, because the Pauli exclusion principle forbids two electrons from inc occupying the same quantum state. Electrons are fermions, particles that obey specific statistical rules, and those rules prevent them from being packed infinitely tightly together. At normal densities, this pressure is negligible compared to thermal pressure from hot gas. But at extreme densities, reached in stellar cores, when matter is compressed to the point where electrons are nearly touching degeneracy, pressure becomes the dominant force, resisting further compression. Right now, deep in the core of Stephenson, 218, 20,000 light-years away, iron is accumulating. The silicon shell surrounding that core is fusing silicon into iron at tremendous rates, adding new material to the growing iron sphere every second. The iron core is getting larger, more massive, more compressed, under the weight of all stellar material pressing down on it from above. There is a limit, a threshold called the Chandrasekhar limit, after Indian astrophysicist Subramanian Chandrasekhar, who calculated it in the 1930s, beyond which electron degeneracy pressure can no longer support the iron core's mass. That limit sits at approximately 1.4 times the mass of our Sunday. When the iron core accumulates enough material to exceed this threshold, roughly 1.4 solar masses compressed into a sphere, perhaps the size of Earth, electron degeneracy pressure fails catastrophically. The electrons can no longer resist compression. When that support fails, nothing remains to hold the core up against gravity. Nothing can stop what happens next, and what happens next will be visible across the entire galaxy. When the iron core of Stephenson 218 crosses 1.4 solar masses, when it accumulates that fatal threshold of material, the core collapses in less than 1 second. Trillions upon trillions of tons of iron implode at velocities reaching 1/4 the speed of light, 46,000 miles per second. In the time it takes you to blink, the core shrinks from the size of Earth to the size of Manhattan, then to the size of a city block, then smaller still. Gravity overwhelms every other force in nature. The electromagnetic repulsion between atomic nuclei, strong enough under normal conditions to prevent atoms from touching each other, becomes irrelevant. The quantum mechanical pressure from electrons trying to maintain their separate quantum states gets crushed into submission. Electrons are forced into direct contact with protons, and under the extreme conditions they merge through a process called electron capture. An electron and a proton combine to form a neutron plus a neutrino. The neutrino escapes, carrying away energy. The neutron remains, joining an ever-growing mass of neutrons, packed together so tightly they're essentially touching. The collapsing core doesn't stop when it becomes neutrons. It continues falling inward, compressing to densities that don't exist anywhere else in the universe except inside black holes and neutron stars. Matter reaches nuclear density, the same density found inside atomic nuclei, where neutrons and protons normally reside. At this density, a sugar cube of material would weigh as much as all of humanity combined, approximately 1 billion tons compressed into less than a teaspoon. The laws of physics that govern normal matter cease to apply. This isn't gas or liquid or solid or plasma. This is a fundamentally different state of matter, neutron-degenerate matter, where the fabric of space-time itself bends and warps under the extreme mass density. The collapse halts abruptly when the core reaches nuclear density, because neutron degeneracy pressure, even stronger than electron degeneracy pressure, suddenly kicks in with tremendous force. Neutrons, like electrons, are fermions, obeying the Pauli exclusion principle. When compressed to the point where they're essentially touching, they resist further compression with a pressure so intense it can momentarily halt the collapse of an entire stellar core. The core rebounds slightly like a basketball dropped on concrete. It compresses on impact, then bounces back. Except this basketball weighs 1.4 times what our entire sun weighs, and it's moving at 70,000 kilometers per second. The outer layers of Stephenson 218 don't know the core has stopped. Nobody told them. They're still falling inward at 70,000 kilometers per second, 21,000 miles per second, roughly 10% the speed of light. Imagine the mass of our entire sun, all 900,000 trillion kilograms of it falling inward at 21,000 miles per second, and then hitting a wall harder than diamond, denser than anything that exists in normal experience. The infalling material slams into the neutron core with such force that it rebounds outward in a shockwave, traveling at 30,000 kilometers per second. This shockwave tears through the star's layers like a tsunami through a coastal town, except the tsunami is moving at 10% light speed and contains more energy than our sun will radiate in its entire 10 billion year lifetime. Silicon layers vaporize instantly, their atoms torn apart by the violence of the passing wave. Oxygen layers explode, dissociating into individual nuclei. Carbon, helium, hydrogen, everything is ripped apart and flung outward at significant fractions of light speed. Material that took millions of years to gradually accumulate through stellar evolution is destroyed and ejected in seconds. The shockwave carries tremendous energy, enough to blow the star apart, but it doesn't carry most of the energy released during core collapse. That distinction belongs to neutrinos, ghost particles, that barely interact with normal matter particles, so ethereal that trillions of them pass through your body every second from the sun without you noticing, because they pass right through without hitting anything. During core collapse, neutrinos are produced in numbers that defy comprehension, released through the electron capture process, as electrons merge with protons to form neutrons. The collapsing core produces more neutrinos in 1 second than the sun will produce in its entire 10 billion year lifetime. So many neutrinos are created traveling outward at light speed that even though each individual neutrino has only a tiny probability of interacting with matter, their sheer numbers mean they deposit enormous energy in the star's outer layers. Neutrinos carry 99% of the total energy released during core collapse, a number so large it's typically expressed using scientific notation, because writing it out would require dozens of zeros. That energy heats the outer layers of the star to billions of degrees, contributing to the explosive disruption of the stellar envelope. The combination of the mechanical shockwave from core rebound and the energy deposited by neutrinos tears Stephenson 218 apart. The star doesn't just explode, it detonates like a hydrogen bomb the size of a solar system. Within hours after core collapse, the shockwave reaches the star's surface 2 billion miles from the core and breaks through into space. The star's outer envelope, containing perhaps 20 to 30 solar masses of hydrogen, helium, carbon, oxygen, and heavier elements, is ejected outward at velocities, reaching 15,000 kilometers per second, 5% the speed of light. This is a supernova, specifically a Type II supernova, because it occurs in a massive star that still retains its hydrogen envelope. For a period of weeks, this single dying star will outshine the entire Milky Way galaxy. The Milky Way contains approximately 200 billion stars, all of them together, producing a certain amount of light enough to be visible as a faint smudge from millions of light years away in distant galaxies. For a brief period, Stephenson 218 alone will produce more light than all 200 billion stars combined. One star, in the final moments of its existence, briefly outshining an entire galaxy. The peak brightness occurs within a few days of the explosion, as the ejected material expands and cools, converting its kinetic energy into light. At peak, the supernova might reach absolute magnitude -19, meaning if you placed it at a standard distance of 10 parsecs, about 32 light-years, it would appear as bright as a crescent moon in Earth's sky. From Earth's actual distance of 20,000 light-years, the supernova will still be extraordinarily bright. Even through the dense walls of cosmic dust that currently hide Stephenson 218 from optical telescopes, enough light will penetrate for the explosion to be visible to the naked eye. A new star will appear in the constellation Scutum, in a region where previously nothing was visible. It will be bright enough to see even from light-polluted cities, bright enough to cast shadows at night, possibly bright enough to be visible in broad daylight like Venus at its brightest. The light will arrive suddenly from our perspective, though the explosion will have actually occurred 20,000 years earlier. If Stephenson 218 exploded today, we wouldn't know for 20,000 years, not until the light traveled the entire distance between the star and Earth. By the time we see it, the explosion will be ancient history. Humanity might be gone by then, or we might be so technologically advanced we're unrecognizable, or we might have spread to other star systems and be watching from multiple perspectives across the galaxy. Whenever we see it, it will mark a moment of cosmic significance. Supernovae are more than just spectacular light shows. They're foundries, factories where elements are created. In the final moments of core collapse and explosion, when temperatures reach 100 billion, Kelvin and neutrons flood the environment in unimaginable numbers. Nuclear reactions occur that cannot happen anywhere else in the universe. Elements heavier than iron, gold, platinum, silver, uranium are forged in these extreme conditions through rapid neutron capture processes, where atomic nuclei are bombarded with so many neutrons so quickly that they transmute into kinrogs, progressively heavier elements, before they have time to decay. Every atom of gold in every ring, every necklace, every coin that has ever existed was created in a supernova explosion. The process requires conditions so extreme they only occur during the final seconds of a massive star's life, when core collapse floods the stellar interior with neutrons moving at significant fractions of light speed. Iron nuclei already present in the collapsing core capture these neutrons one after another in rapid succession, transmuting through progressively heavier elements, iron to cobalt, to nickel, to copper, to zinc, continuing up the periodic table through dozens of elements, each capture adding more mass, until reaching the heaviest stable and unstable elements, including gold, platinum, thorium, and uranium. This process happens incredibly quickly over timescales of seconds, because the neutron flux during core collapse is so intense that nuclei don't have time to beta decay between captures. Under normal conditions, when a nucleus captures a neutron, it often becomes unstable and decays. A neutron transforms into a proton plus an electron, changing the element's identity. But during the rapid neutron capture that occurs in supernovae, neutrons pile onto nuclei faster than decay can occur, building up extremely neutron-rich isotopes that then decay later after the explosion, transforming into the stable, heavy elements we find in nature. The iron in your blood, every molecule of hemoglobin carrying oxygen through your veins right now, was created in the core of a star that died billions of years ago. That star reached its critical mass, its iron core collapsed, and the star exploded, scattering iron atoms into space. Those atoms drifted through the galaxy for millions of years, eventually becoming part of the gas cloud that collapsed to form our solar system 4.6 billion years ago. They were incorporated into the protoplanetary disk, became part of the material that coalesced into Earth, and billions of years later, through processes involving plate tectonics, ocean chemistry, and biological evolution, those specific iron atoms ended up in your bloodstream. The calcium in your bones, every bit of structural support holding you upright, every tooth in your mouth, every signal transmitted between neurons through calcium ions, came from stellar nucleosynthesis followed by a supernova explosion. Calcium is produced through carbon and oxygen fusion in massive stars during the final stages before core collapse, then scattered into space when the star explodes. The calcium atoms in your skeleton have existed for billions of years, cycling through stars and interstellar space and solar systems and planets before becoming part of you. The oxygen you're breathing right now, the oxygen that combines with glucose in your cells to provide energy through cellular respiration, the oxygen that makes up 65% of your body mass, every single oxygen atom was created inside a massive star through helium burning and subsequent fusion processes, then released into the galaxy through a supernova explosion. Before our sun formed, before Earth existed, before the solar system condensed from a rotating disk of gas and dust, these oxygen atoms floated freely through interstellar space, gradually mixing with hydrogen and other elements waiting to become part of something new. Carbon forms the backbone of every organic molecule in your body, every strand of DNA, every protein, every carbohydrate, every lipid making up cell membranes. Carbon is produced through helium fusion in stars, through a process called the triple alpha reaction, where 3 helium nuclei combine simultaneously to form 1 carbon nucleus. This reaction requires extremely specific conditions, a resonance at exactly the right energy level that allows the reaction to proceed efficiently. If that energy level were slightly different, carbon wouldn't form efficiently, and carbon-based life as we know it wouldn't exist. The carbon in your body was created in stars, ejected into space through stellar winds or supernova explosions, and eventually incorporated into the molecular clouds that formed our solar system. When Stephenson 218 explodes, it will eject perhaps 20 to 30 solar masses of material into space, an amount of matter weighing as much as 20 to 30 suns, containing every element from hydrogen up through uranium. That material will plow into surrounding gas clouds at thousands of kilometers per second, compressing them, triggering new episodes of star formation. The shock wave from the supernova acts like a cosmic construction crew, compressing diffuse gas until it becomes dense enough to collapse under its own gravity and form new stars. Over millions of years, the ejected material will slow down, will mix with existing interstellar gas, will gradually disperse across hundreds of light years of space. Some of it will become part of giant molecular clouds, those stellar nurseries where new stars are born. When those clouds collapse, when gravity pulls them together, and fusion ignites in their cores, when planetary systems coalesce from the leftover material, those new solar systems will contain atoms from Stephenson 218. Rocky planets will form from the heavy elements, the iron, silicon, oxygen, magnesium, all the materials you need to build a terrestrial world. Atmospheres will form from lighter elements, nitrogen, oxygen, carbon dioxide. Billions of years from now, on a planet orbiting a star that hasn't formed yet, made of atoms currently locked inside Stephenson 218, something might wake up. Some configuration of atoms might become complex enough to process information, to respond to environment, to reproduce, to evolve. Perhaps that something will eventually become intelligent, will look up at its night sky, with whatever sensory apparatus it possesses, will wonder about. Those points of light will develop instruments to measure them, will discover that it's made of recycled star material. That future organism, if it exists, if it ever comes to be, will owe its existence to Stephenson 218. The atoms making up its body, the planet it stands on, the atmosphere it breathes, all of it will contain material ejected from this dying star. The cycle of stellar birth, life, death, and rebirth has been operating for over 13 billion years since the first stars formed in the early universe. It will continue for trillions of years into the future, until the universe expands so much that gas becomes too diffuse to form new stars, until the last star burns out and the cosmos goes dark. You exist because stars before our sun died and seeded space with heavy elements. The planet beneath your feet is made of supernova debris. The air in your lungs was exhaled by dying giants. Everything you touch, everything you see, everything you are recycled, stardust, ancient beyond measure, forged in violence, reborn in you. Stephenson 218 will contribute to this cycle, will scatter the raw materials of existence across the cosmos, will seed the formation of future worlds and possibly future life. When you die, the atoms that currently make up your body will be recycled. They'll decompose into soil, might be taken up by plants, might eventually become part of other organisms. Over geological timescales, through plate tectonics and erosion, they might be subducted into Earth's mantle, might return to the surface through volcanism. Over cosmic timescales, when the Sun eventually becomes a red giant and engulfs Earth, those atoms might be ejected back into space through solar winds. They might become part of the interstellar medium, might eventually be incorporated into new stars forming trillions of years in the future. Your atoms are older than Earth, older than the Sun, and they will outlast both by incomprehensible spans of time. You are not separate from the universe. You are what the universe is doing right here, right now, at this particular location in space and time. You are a temporary configuration of matter that has become aware of itself, capable of contemplating its own existence and its place in the cosmic scheme. That awareness, that capacity for understanding, exists nowhere else we know of, making consciousness perhaps the rarest and most precious phenomenon in the universe. You are standing on a planet 7,900 miles in diameter, orbiting a star 864,000 miles across, in a galaxy 100,000 light-years wide, containing 200 billion stars in a universe 93 billion light-years across, containing 2 trillion galaxies. The observable universe spans 540 septillion miles, a 5 followed by 26 zeros. If you tried to count to that number, saying one number per second, it would take 100 times the current age of the universe just to finish counting. Stephenson 218, with its radius 2,150 times our Sun, could contain 10 billion suns in its volume. If you tried to count every square mile of its surface area, one number per second, it would take 50 billion years longer than the current age of the universe by a factor of 3. You will live perhaps 80 years. The universe has existed for 13.8 billion years. Your entire lifespan represents 0.0000006% of cosmic history. You are 1 second in a life spanning 500 years. In the time it takes light to cross Stephenson 218's diameter, 8 hours. At the fastest speed physically possible in the universe, empires rise and fall on Earth. Species evolve and go extinct. Languages develop and die. Out. The star is so large that human timescales become laughably inadequate for describing its features. A single convection cell on its surface, one bubble of rising hot gas, measures 93 million miles across and takes months to complete one cycle. If you could watch Stephenson 218 in real time, you would see almost no movement would need to observe for weeks before noticing any change in surface features. You are insignificant on cosmic scales, temporary beyond measure, tiny, to the point where the words fail to capture the disparity. If you disappeared tomorrow, the universe wouldn't notice. Stars would continue burning, galaxies would continue colliding. The expansion of space would continue accelerating, driving everything apart, and none of it would be affected in any way by your absence. You occupy an infinitesimally small volume of space for an infinitesimally small duration of time. And from the universe's perspective, you might as well not exist at all. Yet, with minds that fit inside skulls, the size of grapefruits, using instruments smaller than houses, humans measured Stephenson 218. We measured a star we will never touch, never reach, never see with naked eyes. A star 20,000 light-years away, hidden behind walls of dust thick enough to block all visible light. We calculated its size to within a few percent. Accuracy determined its temperature to within 100. Kelvin measured its distance to within 1,000 light-years, estimated its age to within a few million years, analyzed its composition, and determined what elements are fusing in its core at this very moment. We did this despite being specks, despite being temporary, despite having evolved as savanna-dwelling primates, whose brains were shaped by the need to track game and avoid predators, not to understand stars. Our species developed agriculture only 10,000 years ago. We built the first cities 5,000 years ago. We developed scientific methodology 400 years ago. We discovered that stars are distant suns only 200 years ago. We determined that the universe is expanding only 100 years ago. In that brief span of time, we went from not knowing what stars are to measuring the largest star ever discovered with precision that would have seemed like magic to people living just a few generations ago. The Gaia satellite measures stellar positions so precisely it could detect the width of a human hair from 1,000 kilometers away. Ground-based interferometers combine light from multiple telescopes to achieve angular resolution equivalent to a telescope the size of a continent. Space telescopes observe in wavelengths invisible to human eyes, infrared, ultraviolet, X-ray, expanding our view of the universe far beyond what evolution equipped us to see directly. Spectrographs analyze starlight in such detail they can determine not just what elements a star contains, but in what proportions, at what temperatures, moving at what velocities, in what states of ionization. We developed mathematics sophisticated enough to describe the interior of stars we can never visit, equations that predict temperatures, pressures, densities, and composition from core to surface. We built computer simulations that model stellar evolution across millions of years, following stars from birth to death, testing our theories against observations and refining them when predictions don't match reality. We created entire fields of physics, quantum mechanics, relativity, nuclear physics, specifically to understand how the universe works at scales far removed from human experience. There are 8 billion people on Earth. Stephenson 218 could hold one entire sun for each of us, with 2 billion suns left over. But not one of those suns can think, can measure, can wonder, can know it exists. Those are human capacities, possibly unique in the universe, certainly rare enough that we haven't found evidence of them anywhere else, despite decades of searching. We are specks that can comprehend infinity atoms, that know their atoms matter, that has become aware of itself. We are the universe observing itself, understanding itself, measuring itself, asking questions about its own nature and origin and fate. As far as we know, from 13.8 billion years of cosmic history, we might be the only part of the universe capable of doing this. Consciousness might be an incredibly rare phenomenon, possibly unique to Earth, possibly scattered across millions of worlds, but certainly rare enough that most of the universe consists of unconscious matter, following physical laws without awareness. For 13.8 billion years, Stephenson 218 and stars like it have been burning. For billions of years, they've shone into darkness, their light traveling through empty space, hitting nothing witnessed by no one. Stars exploded, creating and scattering heavy elements. Gas clouds collapsed, forming new stars and planets. Chemistry became complex. Molecules became cells. Cells became organisms. Organisms developed nervous systems. Nervous systems became brains. Brains became aware. After billions of years of unconscious existence, the universe developed eyes and thoughts and questions and wonder. We found Stephenson 218, despite the dust, despite the distance, despite our brief existence and tiny size. We measured it, characterized it, understood it. Being small doesn't make us meaningless. It makes our consciousness miraculous. Being temporary doesn't diminish us. It makes our capacity for understanding precious. Being specks in a vast universe doesn't render us insignificant. It makes our awareness perhaps the most remarkable phenomenon existence has produced. The universe is overwhelmingly empty, overwhelmingly dark, overwhelmingly unconscious. Matter is the exception, not the rule. Structure is rare compared to chaos. Complexity is extraordinary compared to simplicity. Life is remarkable compared to sterility. Consciousness is miraculous compared to the vast unconscious cosmos that surrounds it. We are not at the center of the universe, not important on cosmic scales, not the reason everything exists. But we are the universe's only known way of understanding itself, and that carries profound significance. Stephenson 218 has been burning for 10 million years, pouring light into space at rates 500,000 times greater than our sun, and for most of that time, nothing was watching. No consciousness in the universe knew it existed. No intelligent observer was aware of its presence. It burned alone, completely isolated, separated from anything that might appreciate its existence by distances so vast that even light requires years to cross them. The nearest star to Stephenson 218 sits light years away. If a planet orbits that neighboring star, if you could stand on that planet's surface and look up at the sky, Stephenson 218 would appear as a bright reddish dot among thousands of other points of light. You couldn't see its size, couldn't perceive its surface features, couldn't watch its convection cells churning. Even at distances of light years, even for an object 2,000 times wider than our sun, the the star would be nothing more than a point its disk too small to resolve with the naked eye. You see only the light, never the source itself. Every star in the galaxy exists in this state of isolation. The average distance between stars in our cosmic neighborhood is about 5 light-years, approximately 30 trillion miles of mostly empty space, separating each stellar system from its nearest neighbors. At the speeds we currently achieve with spacecraft traveling at tens of thousands of miles per hour, the journey to even the nearest star would take tens of thousands of years. Voyager 1 launched in 1977, and now traveling at about 38,000 miles per hour relative to the Sun, will take roughly 70,000 years to reach the distance of the nearest star system, Alpha Centauri, and it isn't even heading in that direction. Galaxies themselves are islands separated by enormous voids. The Andromeda Galaxy, our nearest large galactic neighbor, sits 2.5 million light-years away. Light that left Andromeda 2.5 million years ago, when our ancestors in Africa were early hominids, just beginning to use stone tools, is only just arriving at our telescopes now. If we sent a light-speed message to Andromeda today, it would arrive in 2.5 million years, and any response would take another 2.5 million years to reach us. Round-trip communication time, 5 million years. Civilizations rise and fall in less time than that. The expansion of space ensures that most galaxies will never meet, never exchange matter or information, never know about each other's existence. Galaxies are moving apart from each other, and the farther apart they are, the faster they're receding. Beyond a certain distance, galaxies are receding faster than light speed, not because they're moving through space that fast, but because the space between them is expanding faster than light can cross it. Those galaxies are permanently beyond our reach, permanently beyond our ability to observe. Their light will never reach us, no matter how long we wait. Billions of years in the future, as expansion continues, accelerating, driven by dark energy, we don't yet understand, galaxies will be so far apart that each one will be completely alone in an empty universe. An observer in one of those future galaxies will look out at the night sky and see nothing. No other galaxies, no distant lights, just absolute darkness in every direction. They will have no evidence that other galaxies exist or ever existed. The only stars they'll see will be the ones in their own galaxy, and even those will eventually burn out one by one until darkness is all that remains. The universe is overwhelmingly, brutally, beautifully empty. For every atom in your body, there exists roughly 1 billion cubic feet of empty space in the cosmos. Matter represents an infinitesimal fraction of cosmic volume. Nearly all of space contains nothing but vacuum, and the faint afterglow of the Big Bang, that cosmic microwave background radiation, cooled to just 3 Kelvin above absolute zero. If you removed all the stars and galaxies and planets and gas clouds from the universe, if you took away everything except the vacuum itself, you would barely notice the difference, because vacuum already comprises nearly everything. Silence is the default state of the universe. Darkness is the norm. Light and matter and structure are rare anomalies in an ocean of nothingness. This isn't pessimism or nihilism, it's simply accurate description of cosmic reality. The universe doesn't care about our preferences, doesn't organize itself according to what we find comfortable or meaningful. It operates according to mathematical laws that have no opinion about outcomes, yet that very emptiness, that overwhelming darkness, is what makes light beautiful. A candle in a brightly lit room is unremarkable, barely noticeable, its flame competing with countless other light sources. But a candle in a cave, a single flame in complete darkness, becomes everything, the only point of reference, the only source of warmth and visibility, the center around which shadows dance and reality takes shape. The flame means something precisely because of the surrounding darkness. Beauty requires contrast. Wonder requires comparison. You cannot appreciate light without experiencing darkness. Stephenson 2:18 shines brighter because of the void surrounding it. Its light carries significance because it travels through such vast emptiness before reaching anything. In a universe packed with matter and light, one more star would be unremarkable. In a universe that is 99.999% empty space, every star is extraordinary. Every source of light is precious. Every island of matter floating in the cosmic ocean is remarkable simply for existing at all. We are alone in a similar way. Earth is a small planet orbiting an ordinary star in an unremarkable region of an average spiral galaxy. The nearest star system sits over 4 light-years away. If there are other civilizations in our galaxy, and the sheer number of stars suggests there might be, they could be thousands or millions of light-years distant, too far for meaningful communication, given that radio signals travel at light speed and would take millennia to cross even modest galactic distances. We might be the only intelligent observers in the entire Milky Way. We might be one among millions of civilizations. We have no way to know because we haven't found evidence of others yet, despite decades of listening for signals and searching for signs of technology. The Fermi paradox asks if the universe is so vast. If there are so many stars and planets, where is everybody? Why haven't we detected other civilizations? The possible answers range from optimistic, we haven't looked hard enough or in the right ways, to pessimistic, intelligent civilizations are extraordinarily rare or tend to destroy themselves quickly. Regardless of whether we're alone or one among many, we are isolated on timescales and distance scales that dwarf human comprehension. We are separated from potential neighbors by gulfs so vast that even light, the fastest thing in the universe, takes years or centuries or millennia to cross them. We might send messages into space and receive replies thousands of years later, answered by civilizations we can never visit, describing worlds we will never see. But we have each other on this small planet. 8 billion minds are thinking, feeling, wondering, dreaming, asking questions, seeking understanding, creating meaning. We are not alone in our loneliness. We share it with every other human being, every creature that has ever lived, every consciousness that has flickered briefly in the cosmic dark. We look up at the same stars, wonder about the same questions, search for meaning in the same vast silence. We are separated from Stephenson 218 by 20,000 light-years of empty space. We will never visit it, never touch it, never fly through its plasma storms, or watch its convection cells from close range. We will never stand in its light, or orbit a planet around it, or collect samples from its atmosphere. The distances are too vast, the timescales too long, the engineering challenges too extreme for visits to ever be practical. Yet we are connected through understanding, through shared atomic composition, through the same fundamental physics governing fusion in its core and chemical reactions in your cells. We are connected through curiosity that reaches across impossible distances, through the simple act of looking up and wondering what those points of light are, through the sustained effort over centuries to develop instruments and theories and mathematical frameworks capable of answering that question. We measured Stephenson 218 from 20,000 light-years away, using photons that began their journey before human civilization existed, and in doing so, we bridged that gulf, not physically but intellectually. The universe is lonely, profoundly, and overwhelmingly lonely, but we are together in that loneliness. Consciousness might be the universe's response to its own emptiness, a way of creating meaning and connection where none exists automatically. We are matter that has become aware, atoms that know their atoms. The universe understanding itself for a brief moment before the configuration dissolves and the atoms return to unconscious existence. Right now, at this exact moment, Stephenson 218 is burning. Its core is fusing carbon and oxygen into heavier elements, building up the iron sphere that will eventually trigger collapse. Its convection cells are churning, each one larger than Earth's orbit, rising and falling in cycles lasting months. Its surface is radiating 500,000 solar luminosities worth of energy into space as infrared photons that will travel for 20,000 years before reaching any observer. Some of those photons departing the surface right now will arrive at Earth in the year 42,000, long after everyone currently alive has been dead for millennia, long after current nations and civilizations have transformed into something unrecognizable or ceased to exist entirely. Maybe someone in that distant future will detect those photons. Maybe they'll know that Stephenson 218 has long since exploded by then, that the light they're receiving comes from a star that died thousands of years ago. Maybe they'll understand they're seeing ancient history, observing a stellar ghost measuring light from an object that no longer exists. Or maybe humanity will be gone, and those photons will strike an airless Earth, a dead world, with no observers to appreciate their arrival. The star doesn't know you exist. It can't. It has no consciousness, no awareness, no capacity for knowledge or experience. It's a ball of plasma following physical laws, fusing elements because temperature and pressure in its core create conditions where fusion occurs, spontaneously radiating energy because hot objects radiate according to fundamental principles that don't require intention or purpose. The star has no goals, no meaning in itself, no awareness of its own existence or impending death. It simply is existing as a configuration of matter governed by equations. You have awareness. You can look up at the night sky and understand that you're looking at the past, because light takes time to travel. You can comprehend 20,000 light years, can hold in your mind the concept of a star so large it shouldn't exist according to current theoretical models. You can understand fusion and supernovae, and the creation of elements can grasp your place in the cosmic scheme, even if that understanding is imperfect and incomplete. You can know you're not at the center of the universe, can know you're insignificant on cosmic scales, can know the universe doesn't care about your existence, and can find beauty in that knowledge anyway. Consciousness is the gift and the curse, the blessing and the burden. Unconscious matter doesn't suffer because it cannot experience suffering, doesn't feel lonely because it cannot feel anything, doesn't contemplate its own mortality because it has no awareness of existence to lose. Stars burn and die without fear or regret. Galaxies collide without pain. Black holes evaporate without sorrow. The universe operates without caring, following mathematical laws that describe how matter and energy behave under various conditions, but don't have opinions about outcomes. You care. You experience. You suffer and joy and fear and hope and curiosity and wonder. You're capable of contemplating your own existence and finding it meaningful despite cosmic insignificance. You can create purpose in a purposeless universe, can build meaning where none exists, automatically can find beauty in mathematical laws and awe in stellar evolution, and connection in shared atomic composition with distant stars. Stephenson 218 is the largest star we've found yet. It's mostly empty space, 10 billion times our sun's volume, but with surface layers less dense than laboratory vacuum. It's incredibly powerful, producing 500,000 solar luminosities. Yet it will live such a short time compared to smaller stars burning out in 20 million years, while red dwarfs persist for trillions. It challenges physics shouldn't exist according to our models, yet there, it sits burning steadily, completely indifferent to violating theoretical limits. Smallness doesn't mean meaninglessness. You contain atoms from dead stars, calcium from ancient supernovae forms your bones, iron from stellar cores flows through your blood, carbon forged billions of years ago makes up your DNA. Oxygen that was once inside dying giants fills your lungs with every breath. You are literally made of the cosmos, not metaphorically or poetically, but factually and precisely. The universe is not something you're in, it's something you are. You're not observing from the outside. You're a part of it, a temporary, complex, aware part, but a part nonetheless. For a brief moment in cosmic time, 80 years, maybe out of 13.8 billion, you get to look out at the darkness and understand what you're seeing. You get to comprehend stars, and time and distance can hold in your mind concepts ranging from quantum mechanics at scales trillions of times smaller than atoms, to cosmic evolution at scales trillions of times larger than galaxies. You get to wonder, to ask questions that might not have answers, to search for meaning in a universe that doesn't provide meaning automatically. You get to experience the strange miracle of existence, of being a configuration of atoms complex enough to know that it exists. One day, billions of years from now, Stephenson 218 will be gone. Its atoms will be scattered across light years of space, forming new stars and new worlds, and possibly new life. The universe will continue expanding, driving galaxies apart, stretching space itself until galaxies can no longer see each other. Stars will burn out one by one, exhausting their fuel until the last star dies, and darkness claims everything. That ending is trillions of years away, longer than the current age of the universe by factors of thousands, but it's coming. Eventually, the universe will be cold, dark, and dead, just black holes and frozen remnants drifting through an ever-expanding void. But that's trillions of years in the future. Right now, the universe is alive, full of stars, full of galaxies, full of light and heat and motion and possibility. Right now, Stephenson 218 is still there, still burning, still defying the laws we thought were absolute, still producing more energy every second than humanity has used in all of recorded history. And you small, brief, impossibly conscious, made of star stuff, you got to witness it, to learn about it, to measure it from 20,000 light years away, using instruments made of the same stellar debris that makes up your body, to understand it even a little bit, to comprehend its size, its power, its inevitable death, its contribution to future life, to know that when it explodes, it will scatter atoms that might someday become part of other worlds, other organisms, other minds wondering about their own origins. That's enough. In a universe that could have been empty, that could have been devoid of complexity, that could have remained a simple soup of hydrogen and helium forever, we got this. We got stars and planets and chemistry and biology and consciousness. We got to exist, to think, to wonder, to understand. Even if just for a moment, even if just imperfectly, even if our lives are brief and our knowledge incomplete and our existence insignificant on cosmic scales, we gotta be here. We gotta know about Stephenson 218 and billions of other stars. We gotta measure the unmeasurable and comprehend the incomprehensible. We got to be the universe understanding itself matter, becoming aware of matter atoms, contemplating atoms' existence, examining existence, and that miraculous, improbable temporary awareness might be the most beautiful thing in the cosmos, more remarkable than the largest star, more extraordinary than supernova explosions, more precious than all the gold forged in stellar catastrophes. Consciousness is the universe's greatest achievement, the rarest phenomenon it has produced in 13.8 billion years of existence. You are that achievement. Small and temporary, yes, but aware. Capable of understanding what you are, where you came from, what you're made of, how you fit into the vast cosmic scheme. Capable of looking up at the darkness and finding beauty in it, meaning in it, connection in it. Capable of measuring stars you'll never touch and comprehending timescales that dwarf your existence and feeling wonder at scales both infinitely large and infinitesimally small. Thank you for being here. Thank you for existing. Thank you for being part of the universe's brief experiment with consciousness. Look up tonight if you can. Find a dark place away from city lights. Watch the stars emerge one by one until the sky is full of them. Thousands of points of light, each one a sun like ours, or larger, each one burning through its fuel, each one following the same physics. Somewhere in the constellation Scutum, though you won't be able to see it with your eyes, Stephenson 218 is shining, hidden behind dust, impossible, glowing, dying, magnificent. And you're here to know about it, to understand it, to appreciate it, to be amazed by it. Rest well, dream of stars. Remember that you are made of those stars, that you are star stuff, contemplating stars, that you are the universe waking up. And for this brief, beautiful moment, that's exactly what you're supposed to be. Small and temporary, yes, but aware. And in an unconscious universe, awareness is everything.